Hello, everybody, and welcome to the numerical measures part of the descriptive statistics chapter. Last time we talked about plotting, looking at plots at categorical variables and quantitative variables, and went through that sort of thing. And now we are continuing on with descriptive statistics, but looking at some numerical calculations right now and what these measures can do for us. So first of all, I want to say something up front. So this is important notation-wise, that we are going to assume that the numbers we're working with represent sample data and not the entire data for a population, right? All the values for an entire population. It is almost always the case that we will be dealing with sample data. So I'm not going to give you the two formulas and say, okay, this one's for a sample and this one's for a population. I'm not doing that. I'm saying we have sample data. That's what we've got. That's what we're working with almost always. So we'd have different notation is one thing if we were talking about population rather than a sample. We're going to start off with measures of central tendency. And so a lot of what we talk about today, a lot of people will have heard of before and had some practice with before. We are starting off with measures of central tendency, the mean, median, and mode. And the mean and the median will be the big ones for us. And we're not going to use the mode very much at all, but just mention it from time to time, perhaps. So what we've got, we're going to start off with the mean. And I have X bar here. So that's how I'd read this, X bar. That's how we talk of it. And it is the sample mean because we're talking about sample data. So our sample mean, that's our sample mean. It's just the ordinary average. Add everything up and divide by however many observations you have, the sample size. And X bar is a statistic. X bar is a statistic. And X bar, that sample mean, is a lot of the times we're going to use it as an estimator. So it estimates mu. That's the Greek letter mu. Okay, the Greek letter mu. And mu is our population mean. So that's what that's going to mean, and it's going to come up a lot for us in the course, where mu is this theoretical notion that the mean of your entire population, or theoretical mean of a distribution perhaps, that sort of idea. And we're not going to know what it is, and a large part of this course involves estimating the population mean. So our sample mean, which is a statistic, is going to estimate the population mean, which is a parameter. That's something we're going to do a lot of. So we've seen this before, probably since grade 2 or so. Add up all the numbers, divide by however many you have. And our notation for that is X bar. And in statistics, we're almost always summing over all of our observations from 1 to n. So I get a little lazy sometimes and just say the sum of xi over n. If I ever do this, I'm just leaving out the indicator here going from 1 to n because we do that so often. And if it's anything other than 1 to n, I'll bring it up. But this is our sample mean, the ordinary average. We're going to see it a lot. The other one is the median. We've seen the median before, right? The value that falls in the middle when the data are ordered from smallest to largest. If we have an odd number of observations, there is going to be one middle value, so we just pull that middle value. If we have an even number of observations, then we have two middle values. Which one should we pick? Oh, okay, so we say let's take the average of the two middle values, and that's what we do typically here to get the median. So we sort our data from smallest to largest, look at that, rip the middle value if it's odd, average the two middle values if you have an even number of observations, right? So now, if we were to do this, we're going to use the mean more than the median. Just overall, we're going to be using the mean more than the median, especially when it comes to statistical inference procedures. But the median definitely has its place, and we'll discuss some of this along the way. All right, let's just do a quick example here, even though we've probably done this type of thing a few times in our life. Random sample of 5 NHL teams. So I ripped a simple random sample of 5 NHL teams the other day. Got the oldest player on their current roster in years, and this is what we ended up with. And so let's say we wanted the mean, median, and mode of this sample. Well, for our mean, our sample mean of these 5, we can just add them up, right? Add up these 5 values, divide by 5. That's it, right? Our sample size is 5 here. And so we just add up those numbers, divide by 5. We get 34.6, and the units are years, right? So our sample mean has the same units as your original variable. All of these were years, 35 years, 34 years, etc. And so 34.6 years, let's say, right? So the sample mean is always going to have the same units as your original variable. And we can do this in software. So for something like this, it's pretty easy. You can either just punch all those numbers in, or your calculator likely has a function for it where if you input all the values and then ask it for the mean, it'll do that. But a lot of the time we're going to be working with bigger data sets. And so in those spots, we might want to use software like I have here for R, where we either import a larger data set, or for this particular case, I created an R object called NHL oldest, made up of these 5 values, and then I simply used the mean command in R, and R tells me that that mean is 34.6. For the median, well, for the median, we have to order them first, right? So we've probably been doing this for a long time in our lives, but we would order them and say there's 33 is the smallest number, 34, 34, 35, and 37. So there's an odd number of observations. So there's going to be a single median, and it is this value, the third number in the ordered list. So this number here, this is our median. And so the median is 34. There you go. It's this 34 though. We ordered list and we take this one. If we had an odd number of, that was because we had an odd number of observations, it worked out like this. If we had an even number of observations, then we're going to have to average the middle 2. A bit of curiosity here is that we don't have universal notation for the median, or even really all that common notation for the median. Everyone uses different stuff. So one thing that we have, what people use sometimes, is have like an X wiggle, X tilde. But I don't like doing that because it's so hard to differentiate that from the mean if I'm doing this, especially in writing. Visually in this type of environment, that's just really, really bad. So I'm not going to use that. Sometimes people use M. But you know what? Sometimes people use that for the mean. So no, I'm not going to use that either. And then think, hey, what the heck? Why don't we just call it the median? So I'm not going to give it a symbol, and we're not going to use it in formulas very, very often. So we're not going to have a great need for a symbolic representation of the median. So I'm just going to call it the median, and we'll go from there. And this is, of course, also measured in years. The median is 34 years. The mode is the most frequently occurring observation. In situations like this, the mode is not very useful. We're just not typically interested in the mode all that often. And I'll mention the mode in different settings that are a little bit different from sample data, and it come up from time to time. But the mode is not going to be very useful for us. But in this case, we do have 34 occurring twice. So 34 occurs twice, whereas the other values only occurred once. So what the heck, we could say that the mode is 34, but that is not particularly interesting in this particular scenario. So we've got our mean and our median there for a simple little example. And if we were to look for something a little bit more useful, let's take a look at this guinea pig survival stuff that we've been looking at. Plot this histogram, and we had our 60 observations here for our survival times for guinea pigs that had been given tubercle bacilli, an injection of tubercle bacilli in an attempt to give them tuberculosis. And I plotted a histogram. So we've seen this histogram before. But typically then, if we want these values, the mean and the median for something like this, or especially if we have an even larger data set, we're going to want to use software for that. So I went into R and I had the lifetimes in something called GP lifetimes, and so I just asked R the mean of those lifetimes, which is 241.2 days, and the median lifetime, which is 214.5 days. So I had to put it into software. There's no way to tell precisely what those values are from the histogram, but we should be able to tell approximately, because the median is going to be the point here that splits it such that 50% of the observations are to the left and 50% of the observations are to the right. Don't get deceived in thinking it's halfway along between 0 and 600. That's not how it works. That's something different. Okay, that's something different. You know, we could, if halfway between the smallest value and the largest value is something we call the mid-range, but that's neither here nor there for us right now. What I'm getting at is, don't be deceived into thinking the median is halfway. That might be, but sometimes depending on your data, but it is going to be the point such that half the observations are to the left and half the observations are to the right. We couldn't tell precisely where it is just by looking at the histogram, but we could tell if we did some counts that it's got to be somewhere in there. Now, same idea for the mean. We can't tell precisely what the mean is, but we might know in this case, notice that the mean is 241.2. So my mean is 241.2. The median is 214.5. The mean is actually a fair bit bigger than the median here. The mean is actually a fair bit bigger than the median. And that's going to be what we typically see here when we have stuff that is skewed to the right, or if we have a big outlier on the right side, or that sort of thing. Those extreme values are going to have more of an impact on the mean than the median. If we have extreme values, they're going to have more of an impact on the mean than the median. So that's what's happening here. Those values in the right tail, in this right skewed distribution, are drawing that mean farther out to the right than the median. And if we thought about that, if we just go back, let's say we go back to our NHL players for a moment. If we looked at this, and let's take the extreme case. Let's just take the extreme case that if we were to put in 370, say, instead of 37, let's just say, right? We had that. It's not going to be the case for 370 years old, right? But that type of thing can happen, that we get extreme values. If we change this one to 370, the mean's going up a lot. The mean's going up a lot because that 370 is playing a role there. Right, it's going to go up a lot. But the median isn't going to change at all. If we change this to 370, the median wouldn't change at all. So those extremes have a much greater impact on the mean than the median. The mean uses every bit of information in that data, like every one of these numbers. And so you can think of it like that mean is using that extra information in a sense. The median uses it when ranking, but then only uses the middle value. So these extreme values, if for 37, it could be 63 or 48 billion or whatever. As long as it's bigger than 34, your median is going to be the same. So the mean is more impacted by those extreme values in the data set. And that's what we get here. So this under this right skewness, you're going to tend to have the mean being greater than the median. And so in situations where our skewness is extreme enough, we say, well, maybe that mean isn't really the greatest measure. Right? Maybe if we're taking average salary at a company and including the CEO there that makes just a ton more than the people on the floor, maybe that skews things so much, it throws things off so much, that maybe the median is a better representation there. They're both valid. The mean's valid, right? It is what it is. Add them all up, divide by however many you have. But sometimes it can give a bit of a distorted view. So in right skewed distributions like this, the mean, we'll typically see the mean being greater than the median. And if we look at this, so we'll look at a couple different ones, but let's just say perfectly symmetric for now. So let's drop down to this one. In a perfectly symmetric distribution, the mean and the median are going to be exactly the same if it's perfectly symmetric. Now, sample data is not typically going to be perfectly symmetric and not perfectly symmetric very often at all. But if it's, we can still think of it though, if it's roughly symmetric, then the mean and median will be roughly the same. But when you have this more skewness, the values, those extreme values in the tail, are going to have more impact on the mean than the median. And so we see this in this other thing here. If we have this left skewed distribution, so I have the left skewed distribution stretched out this way. Once again, the median splits it 50% of observations to the left, 50% of observations to the right. You can't tell exactly where it is by the histogram, but we could get a pretty good idea counting up, right? Counting up and figuring out that it's somewhere in there. So the numbers I give here are based on the actual calculation of the numbers we used to get the histogram. But the big lesson here is that the mean, once again, is to the left of the median, because once again, it is pulled out by these extreme values in the left tail. Those extreme values have this impact on the mean, this influence on the mean, and are drawing the mean out towards them. So symmetric distribution, if it's perfectly symmetric, mean and median equal. Approximately symmetric, mean and median approximately equal. But left and right skewness, those extreme tail values will draw the mean toward them. Okay, so getting to measures of variability there, but I'm just going to bring up one thing here to note that when I say the mean, so this mean, when we're talking about the mean that we've been going through here, there are different means. Some of you may have be familiar with all of this. There's a thing called the geometric mean. There's something called the harmonic mean. You could have trimmed means. There's some different means that are useful in different settings. This one is specifically the arithmetic mean. And when I say mean, I'm talking about that. I'm talking about the arithmetic mean. So there's other means, geometric mean, harmonic mean, useful in different spots. But we're going to be talking about this one. Okay, now measures of variability. So the variability of a data set, really important in all sorts of things. Later on when we're doing statistical inference, it will impact how precisely we can estimate parameters. If there's lots of variability, then there's lots of uncertainty, and we're going to have a tougher time pinning down the value of a parameter. And in industrial processes, you're trying to fill your cereal boxes, say, they want that variability to be low. You don't want a whole pile of underfilled boxes and a whole pile of overfilled boxes. Some consumers mad. Sometimes you're putting in too much and costing yourselves money. You want variability to be low. Sometimes this comes at a cost, and so the variability overall is an important notion. Financial markets, the pricing of stock options, variability is a huge thing there. Okay, our simplest measure of variability is just going to be our range. The range, and we're going to call it just the maximum minus the minimum. And so trivial data set to start. If we had this a simple data set of size 4, well, our range in this particular case, the largest value, which is 48, minus my smallest value, which is 25. And so overall, I get a range of 23. Now, that's not very informative. Sometimes the range is helpful in certain spots, and we look at it sometimes, okay? And sometimes out there in the real world, when people say range, they're talking about the two values themselves, the maximum and the minimum. So you got to be a little careful, right? So you do have to be a little bit careful. I'm using it in the context of the difference. Sometimes people use it in the context of the two values. This doesn't tell us too much about the variability. Doesn't tell us too much about the variability. Like if we look at this, all that matters is the biggest value and the biggest value here and the smallest value, and there's infinite ways we can place two other values in there. So it's telling us something, but there's infinitely many data sets. 37.3895, 31.264 say that fit in between there. We could keep going. So the range is a useful thing to know, but not super helpful for us. The best measures of variability are going to be based on what we call the deviations from the mean. So the individual value, so the ith deviation is going to be x sub I, that individual value, minus x bar. So the value itself minus the sample mean. For this data, if you crank through that, you'd see that the sample mean is 38. Okay, so that's kind of getting ugly. Let's just do it again. X bar. The sample mean, I can't believe I did that. Okay. One more time. It's going to happen. One line, two line. Okay, so my sample mean is actually 38. So each value has a deviation associated with it, and I mapped it out here. So that's my sample mean, right? My X bar there. And I put in these values, the 25, the 33, the 44, and the 48, and illustrated that these deviations are how far the value is from the mean, but also the sign. So if the value is less than the mean, it's got a negative deviation. If it's greater than the mean, it has a positive deviation. And we might notice quickly that the negative ones added up are minus 16, and the positive ones added up are positive 16, and that is not a fluke. That is a property of that. Every time we sum up all of the deviations, we are going to get 0. So the sum of xi minus x bar for any data set are going to be equal to 0. So little homework, you can show that for yourself, carry that summation through, it pops right out. So the sum of the deviations for any variable always going to be 0. So our measures of variability are based on that, but what are we going to do with them? We can't just add them up. That doesn't do us anything because it's always a 0. So what we do is, well, we're going to have a main thing, but this, to introduce it here, we're going to say, hey, there's those negative ones, there's those positive ones. The magnitude is telling us something about the variability in the values. So why don't we take the absolute value of those deviations? Why don't we just take the magnitudes, take the average magnitude, and call that the mean absolute deviation? Take the absolute value of the deviation, each one, take the average, mean absolute deviation. Now, sometimes a mean absolute deviation, this isn't a unique definition. Sometimes people define it to have the median as the difference, that sort of thing. Don't worry too much about that because we're not going to use it much. So I'm introducing it here, the notion that this would be something. This gives us the average distance from the mean. That's something. That's telling us something about the variability. We could calculate it for this, go through and do that. It tells us something about the variability. But it's just not very useful in a mathematical sense, typically. Our formulas that we do later on and the things that we work with and measures of variability, they don't really use this. It's something we could do. It's not a terrible thing. It's conceptually an easy measure of variability because we're talking about the average distance from the mean. And I think we can sort of get a pretty good grasp of what that is. But unfortunately, it doesn't have very nice mathematical properties, and we do something else. So, the usual measures of variability are based on the squared distance from the mean. So rather than take the absolute value, we square the deviation, and then we add it all up. And this we're going to call the sample variance. So that's our sample variance, and that is a statistic. So based on sample data, that's the sample variance. Now we have this bit of a quirky notion here where we're not dividing by n, we're dividing by n minus 1. We're not taking the average like up there. We're dividing by n minus 1. What's going on there? Well, I have a video and a section in the text going right through that and talking about all of that in fine-tuned detail if you would like to know. But I'm not going to get into that too much here. What I'm going to say is that, first of all, s squared, this sample variance, what it's going to do for us is going to estimate sigma squared, which is going to be our population variance. In the same way that x bar, our sample mean, estimated our population mean, s squared is going to estimate the population variance. And what happens, this notion, if we think about this, there's various ways of describing this, but just overall, if we were sampling from just infinite population, and we're doing all of this, and we would ideally like to put mu in here, the true population mean. And if we were able to put mu in there, the true population mean, then we would divide by n. We take the average squared distance from the mean. But we're not able to put mu in there because we don't know what mu is. I can't put mu in there. So I put in x bar, which estimates mu. Sounds good. Not a terrible idea. Pretty logical, but something happens. And that something that happens is that when we put x bar in here, it results in this numerator being as small as it possibly can be. Maybe not obvious just looking, but still it's the reality. If I put anything other than x bar, then it's going to be a little bigger than when I put x bar in there. So putting x bar in makes that numerator as small as it possibly can be. And so then if we just divided by n, we'd have ourselves a biased estimator of sigma squared. And this whole thing, this s squared, would tend to be too small. Now, why does n minus 1 work? Well, I have talks of that another day. Watch those videos if you're interested, that sort of thing. Here, I'm going to just say that doing this results in a better estimator for us, a better estimator of sigma squared. And if you want the information, you can go see what I have to say there. So we can still think of this, though, as the average squared distance from the mean. Sure, there's this complicating factor that we have n minus 1. But still, overall, we're going to think of the variance like that. The average squared distance from the mean. And one thing here, I'll mention this, probably the only time I'll mention this, is this notion that we do have another formula. Historically, we like this other formula sometimes because it would help with rounding error, and still can sometimes in coding. Mathematically equivalent, exactly the same thing, okay? This is the same thing, but it's harder to see. It's just harder to see. This one I like looking at, the definition of the sample variance. We can see from this one that we're talking about the average squared distance from the mean, that sort of thing. So I'm not going to bring this one up, but it's historically something that's been used and still has some applications today, or coding things and rounding error and that sort of idea. Okay. Now we're bringing up the sample standard deviation because up here, the sample variance, so wait a minute, we squared things, and that was nice for getting rid of the minus signs, and we got the average squared distance from the mean. But when we're talking about the variance, we've got that problem now where we've squared things. So if our original observations were in days, then the variance is in days squared. If our original observations are in meters, then our variance is in meters squared, and that's kind of hard to think about. So we want to get it back on a level playing field. Let's get it back to having the same units as the original observations and the sample and the sample mean. And we do that by taking the square root. And we call that thing the sample standard deviation. So our definition of the sample standard deviation is simply the positive square root of the sample variance. We take the sample variance, we take the square root. So that's what that is. Now, the smallest possible value for these, we're squaring these deviations and adding them up. So we know that s squared has to be at least 0, and we also know that s has to be at least 0. And they're only going to be 0 if every one of your observations equals the mean, which the only way that can happen is if every one of the observations is the same. So your sample variance and your sample standard deviation have to be at least 0, only equal to 0 if all the values in the data set are equal. Okay, so then as the values themselves get farther and farther from the sample mean, then your sample variance gets larger and larger, and your sample standard deviation gets larger and larger. So once again, your sample standard deviation it has the same units as your sample mean and your original observation, and sigma squared is the population variance, but sigma would be the population standard deviation. So that's going to come up a lot as well. Okay. So our sample standard deviation, the sample standard deviation here, a little sort of bit tricky to think of sometimes and what this means, but let's look at a few things that might help. So first of all, the calculations. Not a bad idea to do this maybe once to get an idea for what's going on, but this is not something that we do. We don't do this stuff by hand. So useful to do it to see that you take each value, you subtract the mean, you square it, each value minus the mean squared, add it up. And for our simple data set up top, that's what we're doing, right? I had my simple data set up top with 44, 35, 25, and 48. This was the simple data set that we had, and our n was 4. So that's what's going on here. 44 minus the mean, which was 38, etc. And then 4 minus 1. So we get this for our variance. We would do this in R using the var command. And so the var of the data values, and so that's what R knows the formula, and so R gets us this. And then if we wanted the standard deviation, we simply take the square root of the variance. So we could tell R to take the square root of the variance, or we have a special SD command for the standard deviation. Okay, so it's not a bad idea to do this once. It's useful, perhaps, to figure out how to use your calculator. Calculators often have built-in functions that will calculate the standard deviation for you, but you sure as heck don't want to spend your life calculating this type of thing. It takes forever, and you'll likely make a mistake. So we do, in the real world, rely on software for this sort of thing. And if you're calculating the standard deviation for a variable sample data that has 80 observations or something, that's rather silly. We use software for that kind of thing. Okay, so that's the basics of the calculation formula and getting it out of R. But let's look at this for our guinea pig survival time data. So in the real world, we're calculating this type of thing and trying to make sense of it, trying to use this information to say something related to our research purposes. So I've gone through and I've done this here. So calculated the mean absolute deviation, and this distance is representing that quantity. So these aren't just random little things. The distance is representing that quantity here. This is the mean absolute deviation. The measurements were in days, and the mean absolute deviation then is also in days. The standard deviation is also in days. And there's no way of figuring out exactly what this is from the histogram. There's no way of figuring out exactly what it is, but I went and did it in R. So I put the original 60 data values into R, get the standard deviation of those guinea pig lifetimes, and R tells me that's what it is. So we're going to just think about this now again. Once again, that standard deviation, we can think of it as the square root of the average squared distance from the mean. Man, that is just not intuitive. It is not the average distance from the mean. It is the square root of the average squared distance from the mean. Now that's a mouthful. That's kind of hard to interpret. So let's think about this, though. A couple of things. Just mathematically, how it turns out, because of that squaring, etc. The standard deviation cannot be less than the mean absolute deviation. So we see that it's a little bigger here. And it's going to be, right? So the standard deviation cannot be less, and it's typically going to be a little bit larger and sort of this kind of order, but it depends on the shape of the distribution and a lot of stuff. I can't give you a perfect general rule other than saying your standard deviation is going to be a little bigger than your mean absolute deviation. So it's kind of hard to think of what exactly that standard deviation means, but if we think of it as a quantity that's helpful mathematically at times and that it's a little bigger than your mean absolute deviation, that's not a terrible way to think of it. But probably a little more useful is this next thing, and something we call the empirical rule. So the empirical rule is but a guideline. It's not a rule. Okay? An empirical rule based on what we tend to observe, empirical observation. Okay, this sort of idea. Rule is probably still not a very good name for it, even though it's qualified by empirical. It is a rough guideline for mound-shaped distributions. So it's actually technically, or the values are coming from, are from the normal distribution that we'll talk about much more later, that bell-shaped curve. But in this context, we're saying if it's just sort of roughly kind of mound shape, these kind of sort of things, then this empirical rule will hold water. And the empirical rule is this. It sort of says three things. That approximately, for these mound-shaped distributions, approximately 68% of the observations lie within one standard deviation of the mean. Approximately 95% of the observations lie within two standard deviations of the mean, and all or almost all of the observations lie within three standard deviations of the mean. You can get values outside of that, and we do. But I'm not going to give you a specific number, because the specific number is based on the specific mathematical details of the normal distribution, and that's not what we're talking about here. We're talking about a rough guideline for mound-shaped distributions. Sometimes people give you a number for the third one. I'm not going to do that. So here we're saying approximately 68%. So 65%? Sure. 72%? Sure. This kind of thing. Just a rough guideline to give us an idea of what that standard deviation means. We're going to have almost all of the observations from three standard deviations below the mean to three standard deviations above. Might be a few outside of there, depends on shape of our distribution, sample size, etc. But overall, you're really going to get almost everything in between that three standard deviations below to three standard deviations above. So it starts to give us an idea of what the standard deviation means. So let's look at this for a sample data set that I made up here. And I've cooked the books. So I've cooked the books here to put some numbers on this. So overall, I've forced it in my sample, my simulated data sample here, that I forced certain things to happen. I made the sample mean be 50. I can do that kind of thing. And I made the sample standard deviation by 10. I can also do that kind of thing. And I happen to have this particular the distribution here. So X bar here is at 50, and one standard deviation below the mean is 40. One standard deviation above the mean is 60. So this type of thing here, we're going to see approximately 68% of the observations. And that's reasonable because this is a mound-shaped distribution. So the empirical rule should be a pretty good guideline here. So we have this notion, and I've got 10,000 observations here. So there's a simulation of 10,000 values. And I forced these numbers to happen. And so we're going to say that approximately 68% of the observations are going to be between 40 and 60. And, well, when I go through and I did it for this particular data set, you can't tell specifically, but when I look at the numbers, 68.3% lie within one standard deviation of the mean. Or in other words, 68.3% were between 40 and 60. And 95.4% were within two standard deviations of the mean. Or in other words, when we went from 30 to 70, right? 50 minus 2 times 10, 50 plus 2 times 10. This, we're talking within two standard deviations of the mean. Roughly, based on the empirical rule, we're going to expect to see around 95% of observations. In this particular one, we saw 95.4% of observations. Similar idea for three standard deviations. We had down to 20 and 80, and that's going to capture almost all of our observations. But we got 10,000 observations, which is quite a few, pretty large sample size, and so a few escaped. In this particular scenario, we have 99.7% of observations between 20 and 80, or in other words, from three standard deviations less than the mean to three standard deviations above, and we happen to get 0.3% of the sample values outside of there. So that's our empirical rule. Now, it specifically applies only to these mound-shaped distributions, these kind of things. That's what it's talking about. But it actually works reasonably well under a little bit of skewness, say. If you have a little bit of skewness, this kind of thing, a little bit of left skewness the other way, that kind of thing, it's still not a terrible guideline. It still tells you something. It's still going to be sort of roughly correct. Then there's questions about, are we missing on the left side? Are we missing on the right side? It's not quite as clean as for nice mound-shaped symmetric distributions, but it's still roughly something. It's still something that can tell us rough idea. So it gives us a little bit of an idea now of what our standard deviation means. Almost all the values lie between 3 standard deviations below to 3 standard deviations above. We start to have a bit of a feel for what that standard deviation means. So what we're going to talk about next, we still have some numerical values to talk about, but we're going to talk about measures of relative standing, because sometimes it's not averages, the actual specific data value that you're interested in. Sometimes the most meaningful thing is how large or small that value is relative to other values in the data set. And for that, we're going to talk about measures of relative standing, and that's for next time.